morning, students. This is lecture number 12 and it is based on some case studies and exercises. So, we will first look at some mathematical model of real life problems and try to model them as linear programming problems. Next, we will study some problems on convex sets and also some problems on convex linear combination of some sets. The idea behind this is to make you understand how actually to solve some of the exercises that are based on the methods that we have learnt in module 1. So, the first exercise is as follows. This is a modeling problem which states that wheat which is produced at the various cities in Punjab, that is Philor, Hoshiarpur and Nakodar, has to be transported to Delhi, Mumbai, Chennai and Kolkata at the following unit cost in lakh rupees. Supply at Philor, Hoshiarpur and Nakodar is given to be 7, 9 and 2 quintals respectively, whereas the demand at Delhi, Mumbai, Chennai and Kolkata is 7, 4, 6 and 1 quintals respectively. We are required to formulate the problem as an LPP and determine the least cost transportation scheduled. Now, the data that has been provided in the problem is shown in this table, where it is a rectangular information giving the cost of transporting 1 unit of wheat from Philor, Hoshiarpur, Nakodar to Delhi, Mumbai, Chennai and Calcutta. Also, the bottommost row shows the demand at the various centers, that is Delhi, Mumbai, Chennai and Calcutta. Or in other words, at Delhi the demand is 8, at Mumbai the demand is 4 and similarly at Chennai it is 6 and at Kolkata it is 1. On the other hand, the supply information, that is the supply at Philor is 7, at Hoshiarpur is 9, at Nakodar is 2. Now, in order to solve this problem, the first step that is required is to define the decision parameters. So, we will define the decision parameters as let Xij be the number of quintals of wheat to be transported from the ith supplying city to the jth demand city. As you know that the cities have been divided into 2 categories. The first is the supplying city, which is the 3 cities in Punjab, and the demand cities are the ones to which the wheat has to be transported. So, all the decision parameters Xij's, they should be greater than or equal to 0 and the I has to go from 1, 2, 3, 4 and j has to go to 1, 2 and 3. Now, the problem says that we have to minimize the overall cost for this transportation problem. The minimum cost can be written as follows: x11 plus 4 times x12 plus 7 times x13 plus 3 times x14, etc. The question is, how did we get this expression? See, we got this expression from the previous table, which is given in this table, that is from Philor to Delhi the cost is 1 unit. Similarly, from Philor to Mumbai is 4 units. So, therefore, x11 has to be multiplied by 1, x12 has to be multiplied by 4 and like this. So, the entire expression for the cost is shown here in this expression corresponding to minimum cost. Then comes the two set of constraints. The first set of constraints are called the supply constraints, which means that the supply at each of the three stations has to be restricted to the availability. So, again going back to the previous given table, if you look at this table, at Philor the availability is 7. So, 7 you cannot exceed more than 7. Therefore, x11 plus x12 plus x13 plus x14 should be less than or equal to 7, and that is what is shown here in the first equation of the first set of constraints. Similarly, for the second row and the third row, we have x21 plus x22 plus x23 plus x24 should be less than equal to 9, and similarly the third row. Now, coming to the demand constraint, at the various demand cities, the constraints are the vertical sums in the given table. So, in the given table, again let us go back to the given table. At Delhi the demand is 8. So, the 8 is the minimum demand. If the supply is such that more can be also provided. So, therefore, we have to impose a greater than equal to constraint, that is x11 plus x21 plus x31 should be greater than or equal to 8, and this is what is shown in the first constraint of the demand constraints. X11 plus x21 plus x31 is greater than or equal to 7. The same can be shown for the remaining 4 cities as well, that is the vertical columns should add up to and should be greater than equal to the demand that is required at the target cities. So, like this we have designed this linear programming problem which consists of 4 times 3 yani ki 12 decision parameters have to be obtained in order to minimize this cost and at the same time satisfy these constraints. So, I hope everybody has followed how this transportation model has been developed. Now, let us come to a second exercise. A dog owner, Mr. Ram, is considering a combination of feeds which he wants to give to his dog, and those feeds are called A and B, and would like to feed the dog at the minimum cost, which also while he is making sure that the dog receives an adequate supply of calories and vitamins. It is noted that the dog requires at least 8,000 calories per day and at least 700 units of vitamins. Another toxic constraint is that no more than 1/3 of the diet by weight can consist of feed A. Based on the data given in the table below, formulate the LPP and use the graphical method to solve it. So, the data can be tabulated in this table. We have the feed A and the feed B, and we also have constraints on the calories per kg and the vitamin per kg. Also, the cost per kg is given corresponding to feed A and feed B. Now, we first need to define the decision parameters, that is, let x1 and x2 be the number of units of the feed A and feed B. The objective of the problem is to minimize the cost. Therefore, the objective function can be written as 10 x1 plus 20 x2. Where did this 10 come from? This 10 came from the data that is given in this table. Now, the feed A has a cost of rupees 10 per kg. Therefore, for x1 units the cost will become 10 times x1, and similarly for feed B the cost will become 20 times x2, and that is the reason why minimum cost can be written as 10 x1 plus 20 x2. Coming to the constraints, we can see that the calories constraint can be written as 2000 times x1 plus 2500 times x2 greater than or equal to 8000. Of course, we can simplify this constraint by cancelling out some of the quantities, and similarly the second constraint is the vitamin constraint, which is 350 x1 plus 175 x2 should be greater than or equal to 700. Now, remember that whenever there is an at least, then that means that it could be more also. So, that is the reason why the greater than inequality has been used. If it is at most in a problem, then less than inequality has to be used, but in this particular problem the at least has been mentioned, therefore, greater than inequality has to be used. The third constraint is the toxic constraint, which can be written like this: x1 is less than or equal to x1 plus x2 divided by 3. Of course, as you know that x1 and x2 should be greater than or equal to 0, because we have defined x1 and x2 as the number of units of the feed A and B. So, number of units cannot be less than 0, that is the reason why x1 and x2 have to be greater than or equal to 0. Now, it is a simple 2 variable problem and we can solve it using the graphical method. The solution is written here, that is 8 by 7 and 16 by 7 with an objective function value of 400 by 4. So, let us try to solve this problem with the help of the graphical method. So, the first constraint can be simplified and can be written like this: 4x1 plus 5x2 greater than or equal to 16. This constraint has been obtained from the given constraint that we have modeled just now. Similarly, the second constraint can be written as twice x1 plus x2 greater than or equal to 4, and the third constraint can be written as x2 is greater than or equal to twice x1, and of course, not to forget the non-negativity constraints. Next, we need to write the problem in the 2-dimensional axis. So, that is what we are going to do. We need to write the constraints on the graph. So, we will write it like this. Now, the first constraint is given to be 4x1 plus 5x2, which is greater than or equal to 16. Now, in order to plot this constraint, we first need to plot the inequality and then later on decide which side of the line is the feasible region. Therefore, in order to plot this straight line, we need 2 points. So, how are we going to obtain them? First, we will put x1 is equal to 0 and get the corresponding value of y. This gives us 16 by 5, and similarly we will put x2 as 0 and this will give us x1 as 4. That means we need to plot the 0, 16, 5 first point, and where is that point? 0 comma 16.5 is something over here, and the second point is 4 comma 0. So, it is over here. Therefore, we will join these 2 points like this. Now, the question arises, which side of the line lies the feasible region, and in order to check this, we will substitute the origin in the inequality. So, we find that 0 0, when you substitute in this equation, you get 0 is greater than or equal to 16. Now, we want to see whether this is true or false, and we find that this is false. Therefore, origin is not in the feasible region. And this means that the feasible region is above the line. Similarly, we plot the second line, and the second line is 2x1 plus x2 is greater than or equal to 4, and as before, if you write x1 as 0, then the corresponding value of x2 becomes 4, and similarly if x2 is 0, then the corresponding value of x1 is 2. That means we have to plot the line joining 0 comma 4 and 2 comma 0. So, 0 comma 4 is over here and 2 comma 0 is over here. So, therefore, we will join these two lines. Next, we need to plot the third line, and what is the third line? The third line is x2 is greater than or equal to twice x1. Of course, before I proceed, we need to find out which side of the line is the second line. So, you can see that the second line also the origin does not satisfy the second line. The origin does not satisfy this line, and therefore, the feasible region is above the line. Then comes the third line, that is x2 is greater than or equal to 2x1. Now, as you can see that this line passes through the origin, and therefore, we need to find out those 2 points which are not origin. So, therefore, how we should do it? We can find out x1, if you put x1 is equal to 1, then x2 becomes 2, and if you put x1 is equal to 2, then x2 is equal to 4. So, in other words, we want to write the line which is joining the points 1 comma 2 and 2 comma 4. So, 1 comma 2 is somewhere over here and 2 comma 4 is somewhere over here. So, therefore, we need to draw the line like this, and in order to make sure which side of the feasible region we are looking at, then we need to substitute some known point. Let us suppose we substitute the point 0 comma 5. So, 0 comma 5 tells us that it is in the feasible region, and therefore, the feasible region is above the line. This tells us that our feasible region is this region. It is a good practice to shade the feasible region so that we can understand what are the various points at which the minima is expected to lie. So, now let us try to find out what are these 3 points of the feasible region. Let us call them A, B and C. So, the point A is given by 0 comma 4 and the point B is given by 2 comma 3 and 8 by 3, and the point C is given by 8 by 7 comma 16 by 7. How did we get these coordinates? You know very well from your high school mathematics that these points can be obtained by solving the two equations which form the point of intersection of these lines. So, I can leave this as an exercise for you to check what are these points. Next comes the evaluation of the objective function at these points. Now, as you know that the objective function is 10 x 1 plus 20 x 2, and when we substitute these 3 points A, B and C, then we get the corresponding value for A as 80 units, for B we get 60 units, and for C we get 400 and divided by 7, which is approximately equal to 57 1 by 7. And in order to see which of these points gives us the minimum, what do we find? We find that this is the point which gives us the minimum. Hence, this is our solution. That is, the dog owner Mr. Ram should consider x1 is equal to 8 upon 7, that is feed A should be 8 upon 7, similarly feed B should be 16 upon 7. So, I hope you have understood how this has been prepared. Next, let us look at the exercise number 3. In this exercise, this is based on the convex sets and the convex linear combination. Now, you will find that the problem says that we have to show whether the given point x given by minus 1 by 2, 1 by 2 and 7 by 4 can be expressed as a convex linear combination of x1 given by minus 1 0 2 and x2 given by 0 1 2 and x3 given by 0 1 1. So, how should we solve it? As you know that the convex linear combination is defined as alpha 1 x 1 alpha 2 x 2 plus alpha 3 x 3 such that alpha 1 plus alpha 2 plus alpha 3 is equal to 1 and all the alpha 1, alpha 2 and alpha 3 are greater than or equal to 0. Now, in order to make sure and to find out whether our given x is a convex linear combination of these points, we will check the given point x is given by minus 1 by 2, 1 by 2 and 7 by 4. This has to be expressed as alpha 1 times x 1, that is minus 1 0 2 plus alpha 2 times 0 1 and 2 plus alpha 3 times 0 1 and 1. Now, as you can see that this is a system of equations in 3 variables and they are 3 equations. So, we can just expand it and get as follows: minus 1 by 2 is equal to minus alpha 1, that is all. The second terms are not existing. Second equation will be 1 upon 2 is equal to alpha 2 plus alpha 3, and the third equation will be 7 by 4 is equal to 2 times alpha 1 plus 2 times alpha 2 plus alpha 3. Now, in order to get a solution of this system of equations in 3 variables is very easy, because as you can see from this equation you can get alpha 1 is equal to 1 by 2. Similarly, if you solve these 2 equations, you will see that you can substitute alpha 1 in this equation, that is you will get 2 times 1 by 2 plus 2 alpha 2 plus alpha 3 is equal to 7 by 4, and this will give you the equation twice alpha 2 plus alpha 3 is equal to 3 by 4. And when you solve this equation and this equation, you will get alpha 2 and alpha 3 is equal to 1 by 4. Please check it. So, therefore, we have found the combination of alpha 1, alpha 2, alpha 3 in such a way that alpha 1 plus alpha 2 plus alpha 3 is equal to 1, and all alpha i's are greater than or equal to 0. This tells us that the given x can be defined as a convex linear combination of x1, x2 and x3. The fourth exercise is that we want to show whether the following set is a convex set or not. The set S is given by capital X such that Ax is less than or equal to B and x is greater than or equal to 0. By the way, what does this remind you of? This is nothing but the feasible region of an LPP, and as you have learnt a theorem which says that the feasible solution of an LPP is a convex set. So, you know that the answer is yes, that this is a convex set, but the idea is that we want to prove whether this set is convex or not, and how it is convex we will see. So, therefore, our set S is given by x such that Ax is less than or equal to B, x is greater than or equal to 0. Remember the definition of a convex set. A set S is said to be convex if for all x1 and x2 belonging to S, we have lambda x1 plus 1 minus lambda x2 also belongs to the set S, where lambda is a number which belongs to, where lambda is a number between 0 and 1. So, in order to show that the set S is a convex set, what we will do? To show S is convex, take any 2 points, let us say x1 and x2 belonging to S. Then since x1 belongs to S, this implies Ax1 is less than or equal to B and x1 is greater than or equal to 0. Also, since x2 belongs to S, this implies Ax2 is less than or equal to B and x2 is greater than or equal to 0. So, in order to show that S is convex, all we need to do is to show that lambda x1 plus 1 minus lambda x2 should also belong to the set S. Therefore, let us try to evaluate this point. Therefore, lambda x1 plus 1 minus lambda x2, since we want to see whether it belongs to S or not. So, therefore, we will operate the operator A, and if we can show that this is less than or equal to B, then we are done. So, let us evaluate this expression. Since A is a matrix and lambda is a scalar, so we can pull out the lambda and inside we can get A x1. Similarly, 1 minus lambda is a scalar, so we can pull out 1 minus lambda and we can get inside A x2, and this is what we wanted. So, now this turns out to be lambda times B. Why? Because this A x1 is less than or equal to B. Similarly, the second term can be written like this, which is nothing but B. This happens, this has been possible only because it is given that x1 and x2 belong to the set S, and therefore, they are less than or equal to B. Now, this entire expression tells us that A times lambda x1 plus 1 minus lambda x2 is less than or equal to B, and by definition this means that lambda x1 plus 1 minus lambda x2 belongs to the set S. Also, you need to show about this x greater than or equal to 0, and it is very clear that if if x1 is greater than or equal to 0 and x2 is greater than or equal to 0, then automatically lambda times x1 plus 1 minus lambda times x2 is also greater than or equal to 0. Hence, our proof is complete. Let us come to the fifth exercise. Solve graphically the LPP given by minimize f is equal to minus 4 x1 plus x2 subject to x1 minus 2 x2 less than or equal to 2, minus 2 x1 plus x2 is less than or equal to 2, and x1 and x2 are greater than or equal to 0, are less than or equal to 0. What will be the solution if x1 and x2 are greater than or equal to 0? Now, this is an interesting problem where you can see that x1 and x2 have been given to be less than or equal to 0. In general, an LPP must have x1 and x2 greater than or equal to 0, but in this example x1 and x2 have been given to be less than or equal to 0. So, the solution is given here, that is the solution is 0 comma minus 1 with f is equal to minus 1, and the second part of this the problem says what happens if x1 and x2 are greater than or equal to 0. The solution to the second part is 2 comma 0 with f is equal to minus 8. So, with this we come to the end of this lecture number 12. I hope you have understood all the exercises that we have studied in this lecture. Thank you.